This lesson is for Advanced Algebra, Lesson 2-1 on direct variation. Students need to be aware of the fact that there are several types of variation that we'll be studying in the next chapter, and the first type that we're going to look at is this type called direct. Direct variation is when both variables that you're working with increase or decrease together. So as one goes up, so does the other, or as one goes down, so does the other. So typically students need to look for that word directly somewhere within the problem that they're working on. So as y varies directly as x, that means that the x will increase and so will the y. There will be a constant involved in the formula called k, and students need to make sure that that is included in every variation problem that they do. The x value or the x variable may or may not have a power attached to it, so students need to just watch out for that when they're working. When the problem says varies directly as x or is directly proportional, those two are interchangeable, and they both mean that the variables will increase together. So in a practical way, think about as you consume food throughout the day, the amount of food you eat increases. As you do that, so does your calorie count for the day. So as your food increase goes up, so does your calorie count go up for the day. So those two variables are both increasing together. So that's a direct relationship between those variables. Another more mathematically related example is example 1. Since 1972 in New York, you can get a 5-cent refund on aluminum cans. Let R be the total refund in cents and C the number of cans you return. Write a direct variation equation to match the situation. You basically have two options here. You can say R equals KC, or you can say C equals KR. Make sure you include the K value in both. So does the refund determine the cans, or does the cans determine the refund? I think most students, as they think that through, realize that the cans determine the amount of the refund. So the can is the independent variable and the R is the dependent. The other thing that they give us in this problem is that there's 5 cents involved, so that's our K value. And so students can write it as 5C, or they can write it in dollars, and they can say 0.05C. So I'd accept all three of those answers as options. And that equation describes this situation. It also says it's direct, so students should know that it means as one increases, so does the other. There's 4 basic steps involved when students are solving direct variation functions, and I took this right out of their textbook. You need to write the general equation. That first step should have only letters in it. Don't forget the K. Then you're going to substitute values from the beginning of the problem to help you solve for K. Once you have your K value, rewrite your completed function with the K value substituted in like we did on the previous one. And then use your completed function to find any other missing values that it asks you for. So let's illustrate those 4 steps in our second example. A certain car needs 25 feet to come to a stop after the brakes are applied at 20 miles per hour. Braking distance, D, is directly proportional to the square of the speed, S. What distance is needed to stop this car after the brakes are applied at 60 miles per hour? I'm hoping that most of my students who are in high school are learning to drive or have received their license. Hopefully students are aware of what braking distance involves. So the first 2 numbers that they give you are a braking distance and a speed. We're going to use those later. Let's focus in on statement number 2 here, or sentence number 2, to help us write a general equation. So the braking distance D is directly proportional to the square of the speed. So I've got basically 2 options there for step number 1. I'm either going to say D equals KS squared, or S squared equals KD. The S has to be squared because it says the square of the speed within the problem itself. And then I need to figure out if the speed determines the braking distance or if the distance determines the speed. And I think you can just tell by looking here that you wouldn't want to solve for S squared. Typically you'd want to solve for D. And the speed does determine the distance. So this is the equation that we're looking for. So that's step 1. It's got all letters in it, and we've utilized all the information they gave us in the second sentence. Second step here, substitute given values into the equation to solve for K. The 25 feet and the 20 miles per hour go together. One is a speed, one is a braking distance. We're going to substitute those in to solve for K. 25 feet is a distance, The speed is the 20. Make sure that you square first and then divide. When you square there, you get 400. Divide both sides by 400. K ends up being 0.0625. If students want to leave it as a fraction in lowest terms, that's also perfectly fine. Step 3 now, we're going to plug that number into our original equation so that our equation is now complete. 0.0625 for K and then S squared. So there's our equation for step 3. The only other piece that we haven't used is the 60 miles per hour, so we're going to utilize that for step 4. Use the completed function to find any other missing values. They want to know what the distance is. So we're going to utilize our formula. We're going to plug in 60 for S, and then we're going to calculate. Make sure that you follow the order of operations here, 60 squared, then times the 0.0625. Notice that we're no longer using the 25 and the 20. We utilize those back in step 2, and we don't need them any longer. So the K is the needed value, and then we plug in the 60 in for S. And then when you calculate here, I believe you get 225 feet. So if you're traveling 60 miles an hour, you're going to need at least 225 feet to come to a complete stop. Students are not required to number their steps. I simply numbered them here to help students track which step we were on. We're going to try one more question here, not a word problem, and I'm going to illustrate again the process. This time, it's not a word problem. This problem simply just tells you what to do. If they give it to you in words, we're going to translate it into symbols. Z varies directly as the fourth power of W. So that means Z is our dependent variable and W is the independent. Don't forget to have a K there. Have to make sure we incorporate the fourth power as well. The first two numbers they give you are the ones you're going to utilize to find the K value. So plug in 80 for Z and 2 for W, and then we're going to calculate here. 2 to the fourth is 16, and 80 divided by 16 . So when we divide both sides by 16, we get a K of 5. So now I'm going to rewrite my equation with the 5 in place of the K. I'm no longer going to need the 80 and the 2, so those are gone. Now I'm going to plug in the final number to solve. So W is 3. Make sure here that you do 3 to the fourth and then times the 5. So 3 to the fourth is 81, and 81 times 5 is 405. I'd like students to try number 13 on their own right now, and then I'll display the answer at the end of the video.